wave characteristic, and also in the meantime they possess a particle property. Now this is actually proved shortly after this proposal in 1927. We know electron is a particle at that time, okay? And around 1900 there, we understand electron is a very tiny particle. And in 1927, an electron produces a diffraction pattern. That is observed in a laboratory. So what happens here is that now you have a tiny particle moving at a very high speed, and you actually see a diffraction. Now diffraction is a property of wave. If you have a pool of water, the water surface is calm, okay, and you put a wood beam in that pool there, okay, and along the wood beam you cut small openings there. Now when you start to do some vibration in the water, in the water there, water waves are being transferred. When the water wave hit that pole, that wood beam that you put in the pole there, the water wave, when it hits there, it will be able to pass through the small opening that you have along the wood beam there. And then on the other side of the wood beam there, you see what we call a diffraction. So we know diffraction is a property of wave. Electron is a particle. Particle exhibit a wave property. And this is where we say, well, taking on the basic ideas of Niels Bohr and de Broglie and Heisenberg, Erwin Schrödinger proposed that matter can actually be, we're talking about matter in the microscopic world, matter can be described as a wave. In this theory, the electron is treated as both a wave and a particle. The famous story of the term the Schrödinger's cat. You say, well, how do you explain a particle, matter being a particle and a wave? Well, I say, well, this is like doing an experiment. You have a box. Inside the box, you have a bottle of poison. Okay. There's a cat inside the bottle. And you know the cat is alive when the box is closed. When you open the box there, and the bottle will be tipped, and the cat is dead. So when you look at it, the cat is not alive. But when you close the bottle, and you hear the motion there, and you see, you know that the cat is alive. But the moment you open the box there, the cat is dead. So in a sense, in between opening and close the box there, the cat is both alive and dead at the same time. That's how we explain the particle and wave duality there. So in this case, an electron is described by what we call a wave function. And that wave function can be used to define a complete system of matter. The energy of an electron, therefore, is quantized, and only certain combinations of quantum number. And this is what we're trying to get to in Chem 101 about the quantum mechanics there. We're trying to get to the quantum numbers that we can use to describe the exact location of the electron there. So based on this, and this is what it looks like when you try to describe the behavior of an electron. Well, in the classical sense of physics there, when you have a ball attached to the spring, and the ball is moving back and forth, okay, and you have wave and particle, when you have an electron attached to the spring there, yeah, well, it has the exhibit of the wave function as well as the property of the particle there. So the particle wave duality there. Okay, so Max Born, another German physicist, actually taken to one step further about the Schrödinger's equation there, and they're talking about the probability density of the electron. So since we can't really measure exactly where the electron, how fast the electron is moving, or where they are, we use probability. So 90–95% of the chance when the electron possesses a certain amount of energy, they will be confined in this particular location, in this particular range. And with a higher energy level, 90–95% of the chance, the electrons will move at a broader space there. So we can actually determine the probability density of an electron instead of telling exactly where they are and how fast they're moving. And so this is because when scientists were trying to do that calculation there, according to the Heisenberg's limit of quantum mechanics, that for a microscopic particle, you cannot simultaneously determine the position and the velocity. And this is the famous uncertainty principle. Now, quantum mechanics is a very complex theory and involves a lot of mathematics in there. And this is the basic equation that describes the uncertainty principle. But again, the scope of this course is to introduce the beginning of the origin of the quantum mechanics there. We have no intention to get into the details there. I know after finishing this class, many of you will fall in love with chemistry. When you take chemistry as a major, later on you will take you will take 2 semesters of quantum mechanics there. Okay, so you'll get a chance to get into the details about quantum mechanics there. So for this particular part of the lecture, we just need you to memorize these 3 equations. Okay, and you'll be able to use these 3 equations to do calculation. We have given you several homework assignments in chapter 7, and using these 3 equations to do the calculation. Okay. And then tomorrow, after the exam, on Wednesday, we're going to pick up this topic there, and we will talk about the how do we use what we have developed in quantum theory? How do we use that theory to understand electron distribution in atoms? Okay. So again, we have an exam tomorrow, and then after the exam is the laboratory. So there is a lab report due, and there will be a quiz for the. There's a lab quiz on the topic on the lab activity that we did last Thursday. Okay. So tomorrow it's the lecture exam in class from 8 to 9, and then from 9:30 to 12:30 we're going to do an experiment. Yeah.